SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to the Groundwater Hydrology and Management course on NPTEL. This is week 2, lecture 1. In the first week of Groundwater Hydrology and Management course, we looked at the course content, the weekly breakup of the classes, and also a small introduction to groundwater. In today's lecture or throughout this week, we will look at the importance of groundwater. So someone might ask us, why are you looking at groundwater? Why do you want to study groundwater? So for that aspect, it is important to understand the relevance of groundwater in hydrology, both internationally and globally, also with the Indian market. Why? Because as I mentioned in my earlier slides, India is the maximum or the most extractor of groundwater in ranked number 1, followed by US and China. Most reports, it's mentioned that India consumes more groundwater than US and China put together. So before we get into the statistics of that, let's understand the water balance. Of the water which is available, 100% of the water, 97% is locked in oceans and seas. So you see vast amount of water which is locked in oceans and seas, and you all know that it is not readily used for human consumption, domestic use, industrial use, and agricultural use. Domestic, when I mean domestic, it is for drinking and also washing, cleaning, bathing, etc. So the available water is very less, approximately 3%. And of the 3%, the freshly available water, only 2% is locked in ice caps and glaciers. So most of the fresh water available, which is 3% of the entire water balance, is already locked in your glaciers and ice caps. It is not readily usable or readily available. What do I mean when I say readily usable? It's in an ice format. So you cannot bring ice to your table and then melt it and use it for drinking. Some countries where they have it very nearby, they may use it. But think about using Himalaya ice water for somewhere in the north or northeast. It's not possible. So what is the next part of the fresh water? Only 1% of the total available, right? So of this 1%, most of the water is groundwater, which is 0.9%, whereas the remaining are in lakes, swamps, and rivers, and other resources. The other resources include biological water stored in crops, plants, fruits, etc. So all the big lakes and rivers that you see in the world can only hold a very small percent of fresh water, which is 0.009% approximately. Whereas your groundwater can hold most of it, right? So that is where, when you talk about fresh water, groundwater plays very key ranking or key importance, both internationally and in India, because this is the water that can be tapped for domestic use, agricultural use, and industrial use. So in this week, what we're going to look at is why and how limited groundwater resources are, the reality of groundwater resources globally. It's not an endless supply of water. It's not as big as the oceans, and seas, which is 97%. It's very, very small when you compare to the net available water on the planet. However, when you talk about fresh water, it is the biggest component. So it is very important to understand the global importance of groundwater resources. We're looking at in this week's lecture. Also encourage students to look in the news articles and also update yourself regularly on the groundwater importance. Issues and concerns will also be discussed in this week, groundwater resources, where it's highly used, why it's highly used, those kind of issues. And concerns because of unsustainable groundwater use. What are the concerns? How much water do we have for the future generation and children? So all these issues and concerns will be discussed in this week. And we'll also look into groundwater footprints. So similar to carbon footprints, similar to water footprints or virtual water, we also have groundwater footprint to understand where or how the water that is taken from one location travels across for as a product or as an economic viability of drinking water or any other use. So basically, how do you take one water and then export it to another region? And also understand how much area contributes to groundwater. So let's look at groundwater resources in the world. So that will be our quick introduction. So what you see here is a big map made by all the major international players who actively work on groundwater protection conservation. For example, UNESCO and IIT, National Association of Hydrologists. And what you see is the world can be mapped predominantly into three categories for groundwater resources. One is the major groundwater basins, which is in blue color. And within the blue color, there are variability in groundwater recharge. How much water can get into the system is kind of a proxy for how much water you can take out. Okay, so that is given as your blue color. And within the blue color, you have different shades of very high groundwater recharge to very low groundwater recharge. So visualize your groundwater storage or groundwater unit as a bank account. That's a simple analogy we can make. So you have a bank account and it is not an unlimited supply. No one is going to be putting money every time without your knowledge. Okay, and it's not unlimited. So it is a constructed limited resource. That is your groundwater. And in that monthly you're putting your salary and then you're taking expenses out now and then using credit card, debit card, ATM, whatever it is. So similarly, you have a groundwater unit and inside comes your recharge, and discharge can happen multiple ways. Your recharge can also be in multiple terms. If you have your bank account, you can get your salary, you can get your interest from your account, you can get your rental that can come into your account. So similarly, visualize a groundwater unit, groundwater storage unit, and inside that there are multiple water that can come in, and same way discharge can happen multiple locations and different rates. So you do have a very high groundwater recharge aquifer or a unit. For now, let's keep it as a groundwater unit. And most of India in the northern part is in the blue color. So let's look at first India and then globally. The Indo-Gangetic plain and the Brahmaputra plains have very fertile resources for groundwater. So you can see the recharge is very high, and the land and environment and hydroclimate is very conducive for water to recharge rapidly. You also get a good rainfall. So that helps in recharging actively the aquifers. So aquifer is the unit for groundwater storage. So similarly in watersheds and hydrology, we saw that you needed a watershed boundary. Here we call it aquifer. So an aquifer is the storage unit for groundwater. So the Indo-Gangetic Brahmaputra aquifers are very highly yielding and very high recharge rates. Whereas most of the other parts of India come under the areas with complex hydrogeological structure. Complex means it has different geological setting, rocks are different, and the storage within the rock is very different. So we will look at it in detail in the coming class when we talk about physical groundwater hydrology. What constitutes hydrology, we will discuss. And also we will look into the different aspects of groundwater recharge. Okay. So you see most of India has a very complex structure, especially in the middle, central and eastern regions. And when you come to southern regions, the complexity is available. Also, the groundwater recharge is very low. And that is where you see a lot of people putting in bore wells, digging new wells, but getting into loss. So this is the scenario of India. We have both the high yielding aquifers or high recharge aquifers, groundwater resources. Also, we have complex groundwater resources where water availability is very low. Then we have some areas with local and shallow aquifers, which is very small aquifers, very localized. It doesn't yield that much recharge, and groundwater is a concern. Okay, so that part you can see here in Gujarat region. Moving across the world, the blue areas, most of European regions, Australia, part of Australia, Africa, the central regions of Africa, South America and North America have good yielding aquifers, good yielding groundwater resources. The recharge rate is pretty high, and this area with all the big rivers and forested ecosystem has a very conducive environment for groundwater resources. In the remaining regions, the area is very localized and shallow. If you look at Canada and Russia, where the groundwater recharge is very low and also very localized because of the geological setting. Most of those areas are frozen, not much agriculture happens, so not much extraction happens, and so the recharge is also very slow. Some central parts of Australia and Africa also come into the picture. Then you have the green areas with a high complex structure, and you could see that most of India comes under it, and similarly Canada, wherever you see a very high complexity, the groundwater recharge is very low comparatively, and storage is very low. So if you look at the Middle Eastern countries, the Arab countries, they also have such aquifers along with Australia. Someone might ask, so groundwater in Africa is very blue in this picture, but still, if you look at images from Africa, they don't have enough agriculture, they don't have enough water, they're struggling for water. What is the reason? The reason is the aquifer is present, groundwater is present at high volumes. However, the way to access it is very expensive. In India, it's very shallow. And so you can put a pump and take it out. Energy is available. You have hydropower, you have solar power for groundwater extraction, diesel power, fossil fuel powered engines, pumps. But in Africa, they cannot afford it. And because they could not afford it, the groundwater resources have not been tapped. So this is the understanding why some regions are still blue and still under the water starvation countries. If you look at European countries, they have very good aquifers or good groundwater recharge, but they also use very less because they don't do much agriculture. Most of the agricultural products are imported, like India supplies, Pakistan, and Vietnam, China, Malaysia, they supply food to these countries. And so they don't grow much agriculture. They don't need that much water. So India is pumping a lot, producing these agricultural outputs and also exporting them. So we'll discuss this in the groundwater. Continuing with major global groundwater resources, there are multiple studies. You looked at the previous slide, we saw many universities, UNESCO, IIH coming together, and IAEA, all these big international agencies coming together to map the groundwater resources. However, there are other agencies and studies like Taylor et al. 2013, they have made also similar maps using different methods. So the methods may not be the same. However, the overall groundwater mapping is similar. You look at their study, the major regional aquifers or major groundwater systems are in dark blue, and they are in India. It is the Indo-Gangetic Plain, some parts of Brahmaputra. In Australia, it is a Great Artesian Basin. Along the African regions, it's the Nubian Sandstone Aquifer System, Northwest Sahara Aquifer System. And in the US, it is the High Plains Aquifer in California, Central Valley. These are very high yielding aquifers. And if you look at these regions, that is where a lot of agriculture also happens. If you come to the South American countries, you have the Guarani aquifer, and in China, it is the North China Plains aquifer. These are the high yielding major regional aquifers. They have high yield and high recharge, and so they support a lot of populations. If you look at the groundwater use in the Ganges Basin, it almost caters to a big population that surrounds the Ganges plain. Okay? It's very hard to put a number, but indirectly the Ganges Basin supports 1 billion population. Okay, and that is with surface water and groundwater resources. Let's move on. The areas with some important but complex aquifers are in the green, as similar to the previous study, and that encompasses most of India and some parts of your European nations, North and South America, Australia, these regions. So they are very complex, and the complexity comes because of the geology, the ground, under the ground, what is available, the rock, the sediments, that determines the complexity. We will get into that when we discuss the groundwater hydrology and physical parameters. But for now, it is better to understand where are the major systems and why are they major, etc. So major also reflects a good, healthy groundwater status. So if you look at most of India, it is under the complex, but the Indo-Gangetic Plain still has a lot of water. Similarly, if you look at the European regions, there's a lot of groundwater. And as I said earlier, there is a lot of groundwater in some regions because they don't use it much. If you come to South America, there's a lot of forest and healthy big rivers that flow like Nile. So what they do is they have a lot of water resources that recharge the groundwater, and also a healthy forest system that supports healthy groundwater. Okay, so there's always a link with the environment and the geology on assessing the groundwater status. Areas of generally low permeability and local aquifers. So local minor, very small aquifers are present in the rest of the world. Iceland, there's no need for looking at it, but and Greenland. But if you look at other regions, there are fairly a lot of complex aquifers, groundwater systems, and mostly localized groundwater systems are present. So what happens with the local is there's a lot of complexity. So a groundwater status, how much water you can extract, might differ from one location to the other location because it is very local and the properties change. So that is what Taylor et al. Shows here in China and most parts of the Americas. You see that it is a very locally aquifer system, locally in terms of very localized in small pockets. And the properties change. So you cannot apply one recharge rate or one yield rate for it. On this note, it is very important to understand the groundwater footprint because, as I said earlier, it is these aquifers are present, but it is also present because they may not be using the water much. So we need to tap on how much water is actually used and what is the footprint. Let's define groundwater footprint as per Gleason et al. 2012. This famous paper argues that groundwater footprint can be coined or determined as the area required to sustain groundwater use and groundwater dependent ecosystem. So ecosystem services is all the biotic and abiotic services or living organisms that need water and contribute to the environment, like worms, trees, etc. So how much water they need, etc., is documented. So the groundwater footprint could be the area that the groundwater aquifer or the groundwater system needs so that it can satisfy all these groundwater system dependent ecosystems. Okay, so it is the area need to sustain the groundwater use. It shows that this study shows that 3.5 times higher than the aquifer, and it supports up to 1.7 billion people. So all the major aquifers they mapped, and they looked at how much area is needed to activity, the current activity in the aquifers. For example, groundwater aquifer or a storage can be used for agriculture, domestic, industrial. So they took account of all this water that is needed, budgeted all the water, and then looked at the area that the groundwater aquifer needs to sustain such use. And what the study found was very concerning because of the groundwater demand. Almost 3.5 times higher is the area that needs to sustain groundwater use. So to visually put it, look at the Ganges basin or upper Ganges basin, the area is 4 times, up to 4 times bigger than your actual groundwater. So to get water into your groundwater aquifer or unit, you need to conserve an area which is almost 4 times. That is the area that is required. So water should be caught, water should be pushed into your aquifer system or infiltrated, recharged, and then the groundwater use. So it's up to 3.5 times. And more importantly, they documented who's using it and what is the population that is directly linked to these aquifers. So the main aquifers are the Western Mexico aquifer, the High Plains aquifer in the United States, the North Arabian plains in the Middle East, and the Persian, along with the Persian aquifers, along with that the Upper Ganges Basin and the North China plains. All the others are aquifers and groundwater systems, but they are not as important or as predominant as these aquifers discussed in this paper. So what these major aquifers are doing are catering to a big population, according to 1.7 billion in 2012. That is almost by saying every 2 people out of 7 are using the groundwater from this region. So at that time, let's approximate the population to be 7 billion. So out of 7 billion, approximately 2 billion people are using water from these aquifer systems or are dependent on these aquifer systems. So it supports these people both for food, for domestic, industrial, etc. And that's where the dependence causes more importance to the aquifers and more land needs to be preserved. So when we have these aquifers in picture, please understand that there are a lot of transboundary aquifers, which means Ganges water can be used by our neighboring countries also. So it is important to understand how much volume does everyone use. So we looked at the different groundwater aquifers in the world. We looked at the groundwater footprint or how much water is being extracted versus the area that needs to be conserved. Let's now look at the actual volumes. Let's put numbers here. And this study by Shah in 2014, Professor Shah collected these values and plotted it very beautifully to show that the volume of water extracted in the by groundwater pumps and other resources is approximately 260 to 255 kilometer cube per year for India. Whereas it is much lesser for other countries, even though it is high. So India is ranked number 1, and the rate is around 260 to 55 kilometer cube per year. Whereas the next country, which is ranked 2, is Americas or United States with around 100 or 110 cubic meter per year, followed by China with around 80 to 90 kilometer cube per year. So if you add all this, you see that the total is still much lesser than the amount water India uses, groundwater. In other words, the groundwater used by India is more than the next two countries combined, which is US and China. But that's not it. Look at the size of the countries. US and India are comparably very, very different in land size. India is much smaller compared to US and China. However, our groundwater use is much, much higher. So this is a concern. Okay, so that's one concern you see from this graph. The other concern you see is most of the Asian countries are still increasing. If you look at India, it's slowly started in the industrial revolution area, and then in the green revolution time, it just picked up and it's still going on. There's no sign of it slowing down, the groundwater volume. Every 10 years, it seems to increase. Whereas the other countries like Western and European countries have almost tapered off. Tapered means it almost stabilizes. Okay, it has hit the peak and it is stabilizing. It doesn't go above a particular level, or it doesn't keep increasing. It is not as increasing, like here we see an exponential increase, whereas this increase is almost stabilized. Same with China, it is increasing, but not as rigorous as India. And other countries like Western Europe is almost coming down in groundwater use, whereas the Asian countries are slowly pulling up. Ghana is coming up, Spain, but most importantly, Pakistan, Sri Lanka are all slowly coming up, and they started to move upwards after 1980s. Whereas India started in 1960s, 1950s, and it didn't even slow down. So this is how countries compare. And as I said, some countries have already stabilized, while Asian countries are still continuing water extraction, which means it's going up. So what does it show to you in a different connotation is that the Western countries are shifting the focus of water, where to use, how to use water, whereas the Asian countries are still using water for agriculture very, very less efficiently, and groundwater is tapped readily without understanding the consequences. So that is a concern, and everyone has to look at it. So, as I said, why these countries are using so much groundwater is a concern. And for that, it is very important to look at what are the key uses for these groundwater resources. Just looking at these nations like India, China, and which other countries, you have Bangladesh, you can clearly understand that there is some trend why these countries use so much groundwater. You should first look at the groundwater use volume. So here we look at it 260 to 55 kilometer cube here in India. And then we should look at what are the key resources that are being used for groundwater, or which are the key users for this groundwater, let's say agriculture, industry, domestic, etc. So if you divide all this, we can clearly understand for each country what is the major use for groundwater, and that we will look in detail in the upcoming in lecture 2. For now, let's stop on understanding where our major user is, which are the key countries that are using this groundwater, and also understand that most countries in the western part are slowing down in groundwater use, or are stabilizing, whereas the Asian countries are still on the up. Is this sustainable is a question that should come out. Is this good or is this bad? So bad as in the sense, can we continue such a behavior of using groundwater without stopping, or can we, or should we stop? So all this we will look into in detail this week. Let's start with the major user for groundwater in the upcoming lecture. With this, I would like to stop the week 2, lecture 1.